Hi everyone. This is going to be a lesson on angle measure for pre-calculus. So if you've been following along with the lessons so far, you know that we've been doing trigonometry. We've been doing the unit circle and the trigonometric functions. So in the book that we're following along with, which is this one, we are about to start a new chapter. So this is 6.1 in the book here by Stewart, Redlin, and Watson. And we're going to be continuing trigonometry, but we're going to be looking at it from a different perspective. Instead of just looking at it in terms of the unit circle, we're going to start talking about angles and triangles. So let's go ahead and get started. Okay, angles and triangles. Well, what we'd really like to do in this chapter, really we'd like to talk about triangles, but you can't really talk about triangles until you talk about angles. So I'm going to start by saying that when we go some distance around the unit circle, as we've been doing in the previous lessons, we have our unit circle and we typically go counterclockwise some distance and wind up at a terminal point. And when we do that, when we go some distance around the unit circle, we create an angle. Now, I think in the lessons up until now, I don't know if we've used the word angle. I've actually tried to avoid using the word angle because it's really the topic of these lessons and this chapter. Let me draw two examples here. I want to show you how going a different distance around the unit circle, a different t value, is going to form a different angle. So what if I went, we use our usual starting point on the unit circle, and we go counterclockwise if it's a positive t value. So let's say I go t equals, can you figure out what t value I'm doing based on where this point is? Pi over 4. All right, so that's one of the common t values that we've looked at. And where's the angle? Where's the angle that we're forming? I want to say that we're forming an angle between the terminal point, the starting point, and the origin. And that I highlighted those 3 points just now, and I'm going to draw, let's get a different colored pen here. I'm going to draw a line from the origin to the terminal point, and also from the origin to the starting point. Okay. That creates an angle, and we say that that angle is 45 degrees. We'll talk a little bit more about degrees soon. I'll show you another example. What if we did a larger t value? What if we went to here? What common t value do you think I'm trying to represent with this picture? It's bigger than t over 4, right? I'm sorry, it's bigger than pi over 4. I went a little further. I'm trying to represent t equals pi over 3 with this picture. Pi over 3 is larger than pi over 4. And if I do the same thing, if I say, all right, does this create an angle with the starting point, the origin, and the terminal point? It would look like this. We say that this is a larger angle. I mean, it was a larger t value. Larger t value seems like it made a larger angle. And it's going to turn out that we're going to call this 60 degrees. Notice that we're going counterclockwise. We're starting from the right. We're going counterclockwise. And right now we've been making small angles that are in quadrant 1. And we'll talk about other angles coming up soon. Now, how did I know this was 45 degrees and how did I know this was 60 degrees? We'll talk about that soon. Before we talk about that, before we actually measure angles, I want to say, what is an angle? We might have kind of an intuitive idea of what we think an angle is. And really, angles are something that you might talk about in a geometry class. So let's talk about this briefly in terms of geometry. I'm going to draw a picture, and then to the right of it, I'll write some words, but we need 3 points. We need a point here, a point here, a point here, and kind of like I did above, we connect these. And for the purposes of this definition, I'm going to call this point A, and this point B, and this point O. Okay? By the way, I'm using O here, not 0. And by the way, the O stands for origin. It's kind of the origin in the pictures above, right? So A could be thought of as maybe where we start from, and B could be thought of as where we end up, and O is the origin. And I drew not just line segments, but I drew arrows at the end of them. So I wonder if you remember from a geometry class, what is it called when you have a line segment, but then it keeps going in one direction? It's called a ray, and I'm going to label it R1 and R2. We have 2 different rays emanating from the origin. An angle, AOB, consists of 2 rays, R1 and R2, with a common vertex O. So the vertex of a ray is basically its starting point. You could think of the ray R1 as starting at the origin, and then it just keeps going in some direction forever. And the ray R2 starts at the origin and then keeps going in some direction forever. We often interpret an angle as a rotation from the ray R1 onto the ray R2. I'm grabbing my pen here, and I'm going to draw a little arrow to indicate rotation. Like that. See what I just did there? So we might think of R1 as sort of the starting ray, and the ray R1 gets rotated counterclockwise and until it matches the direction of R2. So how much did we rotate? That's going to be sort of the measure of the angle. If the rotation is counterclockwise, as we've been doing, the angle is considered positive. Okay, kind of like the t values that we've been talking about. When we go counterclockwise, we say it's a positive t value. If clockwise, the angle is negative. Again, kind of like the t values, you know, that would be like going in the opposite direction. The opposite direction from positive is negative. All right, so we've talked about what it technically means to be an angle in terms of rays, and we interpret it as rotation. And now the title of this section, title of this lesson was angle measure. So we want to talk about how to measure angles, and I'm going to tell you 2 ways to measure angles. And I don't mean like we're not going to we're not going to take out a protractor and like try to measure them in that way. Here, let's draw a picture, and it's going to be similar to the first picture that I drew up above. Unit circle. It kind of seems like we could talk about angles in the unit circle, or we could talk about angles without the unit circle. So we'll be doing both in this section. How about I form an angle formed by t equals pi over 4. I feel like that t value kind of forms an angle. And I'm going to call this angle, I'm going to label it by the Greek letter theta, which I don't think we've used yet in this class, but that's the Greek letter theta. The angle theta, let me write this just so you see, this is theta, is determined by t. The distance we go around the unit circle, right? If we go a larger t value, then it feels like we have rotated further and gotten a larger angle. If we have a small t value, it seems like we have a small angle. We say this angle is, and I'm talking about this particular angle in this example, t is pi over 4, and we wind up saying theta equals pi over 4 radians. Or, I said there are two ways to measure angles. The other way of measuring it is we say theta equals 45 degrees. These are two different units of measurement that are both measuring the same thing. How big is the angle? We also have some ways of abbreviating. When we're measuring things in radians, we might call it pi over 4 rad for short. And when we're measuring things in degrees, we might write 45 with this little degree symbol right after the number, instead of writing out the word. All right, so I'm going to get a fresh sheet of paper. We're going to talk about radians and degrees a little bit more. I mean, kind of a big question right now should be, how do we know that this is 45 degrees? Is it 45 just because I said so? Like, why is it 45? Why isn't it 55? Why isn't it 35? Like, what is it about pi over 4 radians that makes this 45? So we need to talk about that. I think you could see where the pi over 4 radians comes from. The pi over 4 radians was just the t value, which that seems kind of natural to just say, oh, let's just take the t value and say that's how big the angle is. And that's what we're doing. So t was pi over 4. We say the angle formed by this value of t is an angle that's pi over 4 radians. So radians are actually easy. They're just t values. Degrees aren't that hard either. All right, so let's talk about radians. First of all, one complete revolution around the unit circle is, how many radians do you think it is? Well, it's kind of like saying what t value would we need in order to go all the way around the unit circle once, and that's going to be 2 pi. So we could say 2 pi radians. Like complete rotation all the way around the unit circle. I'm going to say this unit of measurement arises naturally. In mathematics, so it is used in calculus. All right, now the class that we're in right now is pre-calculus, so I'm not going to ask you any calculus questions, but we do want to prepare you for calculus, and understanding radians is a part of that. When I say this unit of measurement arises naturally, what do I mean by that? Well, you remember where the t-values came from when we talked about those. You know, the unit circle has a radius of 1, and a circle with a radius of 1 has a perimeter of 2 pi. So it feels like radians are a unit of measurement that we didn't really invent this unit of measurement, right? It just kind of exists. Whenever you talk about a circle with a radius of 1, there are some t-values that come up, like pi over 4, pi over 2, pi, 2 pi. So it's natural to talk about things in terms of radians because they're just lengths of portions of the unit circle. Let's talk about degrees. Degrees, on the other hand, were invented. You know, somebody decided that one complete revolution around the unit circle is 360 degrees. Why is it 360? It's 360 because some people decided it was going to be 360. They said, let's take the circle, the unit circle, or really any circle, and let's chop it up into 360 equal pieces. And each of those pieces we're going to call a degree. It might seem like a pretty large number. Why pick such a large number, 360? And it really comes historically from people who were counting in base 60, and the fact that 60 and 360 have a lot of divisors. 360 is actually a convenient number to use because it's easy to divide this in half. It's easy to divide this into quarters. It's easy to divide this into tenths. You know, 360 has a lot of divisors, so you can chop up the unit circle into 10 equal pieces, 12 equal pieces, 3 equal pieces, right? So it's a pretty convenient number to work with. And it is convenient for real-world applications. Now, when I say that these are two different units of measurement, we could really think of this as kind of like inches and centimeters. You know, they're two different units of measurement that measure the same thing. And because of that, we should be able to convert back and forth. And maybe they have their pros and cons. Maybe sometimes we want to work in radians, and maybe sometimes we want to work in degrees. So we need to be able to convert back and forth. I guess there's already one that we've already done, which is pi over 4 radians is equivalent to 45 degrees. There's another one here. 2 pi radians is equivalent to 360 degrees. But in general, if I said pi over 3 radians, or if I said pi over 6 radians, or some other number, we want to know how to convert. So let's start with the fact that 2 pi radians is equal to 360 degrees. We're going to use this to come up with a way to convert back and forth for any amount. What I'm going to do is divide both sides. This equation is true. I'm going to divide both sides of it by 360. See what I did? Just divide both sides by the number 360. The left-hand side could be simplified. 2 over 360 simplifies. So we get pi over 180 radians is equal to 1 degree. So we could use that maybe to help us convert back and forth between degrees and radians. If you asked me how many radians are in 1 degree, it's this. If you ask me how many radians are in 5 degrees, just take 5 of these. 5 times this. How many radians are in 7 degrees? 7 times this. Right? So that's cool. Another thing that we can do is, let me start with this again. Instead of dividing both sides by 360, I'm going to divide both sides by 2 pi. If I divide both sides by 2 pi, the left-hand side becomes 1 radian. The right-hand side becomes 360 degrees over 2 pi, which means 1 radian is equal to 180 over pi degrees. This is also useful for converting back and forth between degrees and radians. Because if you asked me how many degrees are there in 1 radian, well, 1 radian has this many degrees, 180 over pi of them. If you asked me how many degrees are in 2 radians, 2 radians would be 2 times this. So that many degrees. Here, let's write some of this stuff underneath. 1 degree is pi over 180 radians. And what is pi over 180? Pi over 180 seems, if pi is a little bit bigger than 3, and we're dividing it by 180, this is a pretty small number. And I'm going to tell you with a calculator, I found this to be about 0.01745. You don't need to memorize that or anything. And so what does that say? That says that 1 degree is a very small amount of radians. But that kind of makes sense, right? Because there's 2 pi radians in the entire circle, 360 degrees in the entire circle. So it makes sense that this would be a small little bit of radians. What about 1 radian being equal to 180 over pi degrees? What is that as a decimal? Well, now it's 180 on top, so 180 over 3.1 something. With a calculator, this winds up being about 57.296 degrees. So an angle with this many degrees is an angle that's 1 radian. Okay, so let me reiterate. You don't have to memorize these decimals, but you do need to know that we're working with pi over 180 and 180 over pi. Because pi over 180 and 180 over pi, those are really going to be what we use to convert back and forth. I'll show you an example. 36 degrees. 36 degrees. Let's say how many radians is 36 degrees? Well, I want to convert from degrees to radians. I'm going to take 36 times, which one of these do you think I need to multiply by? It's one of these two. To go from degrees to radians, we multiply by pi over 180. Because 1 degree has this many radians, so 36 degrees has 36 times this. And all that's left is, can we simplify 36 over 180? 36 over 180. Yeah, actually 36 does divide into 180. And this simplifies to pi over 5. But let's write pi over 5 radians. So an angle of 36 degrees is an angle of pi over 5 radians. I'll give you a problem to try. How about this? There's going to be 2 parts to this problem, and I'll do the first part, and then I'll ask you to try the second part. Sounds fair? All right, so example. I'll write both parts first. Express 60 degrees in radians. Part B. Express pi over 6 radians in degrees. And before you try this, I'll do the first part for us. Or you could pause and do both parts if you want. Okay, 60 degrees in radians. It's going to be kind of what we did with 36, right? Same idea. Same idea. So let's just take 60 and multiply it by pi over 180. And then just see if it simplifies at all. 60 over 180. Yeah, that does divide, right? 60 divides into 180 3 times. So this is going to be pi over 3 radians. That's my answer to part A. So go ahead and pause the video and try part B. Okay, part B, we start with pi over 6 this time. We need to multiply it by sort of a conversion factor. This time, instead of pi over 180, we're going in the opposite direction, so we need to multiply by 180 over pi. What's nice about this is the pi over pi cancels out, right? Pi over pi cancels out, you get 180 over 6. Don't just leave it like that, though. 180 over 6, check. Does 6 divide into 180 nicely? Yes, it does. You could do a little bit of scratch work division if you need to, but you might be able to do that in your head. 6 goes into 180 30 times, and our final answer should say 30 degrees. Don't just say 30. Say 30 degrees. It's okay with me if you leave the degree symbol off in the middle of the problem, but your final answer should have the correct units, for degrees at least. All right, so that's converting back and forth. You just have to multiply by pi over 180 or 180 over pi. If it's multiplying by 180 over pi, you often have a pi over pi that cancels out. Maybe not in every single problem, but in a lot of them, there's going to be a pi over pi that cancels out. Note, we often don't write rad. We may refer to an angle as theta equals 30 degrees, or we could just say theta equals pi over 6, period. That's the angle we talked about in part B just a second ago, and we called it pi over 6 radians, or pi over 6 rad. And now I'm saying, this is new for us, I'm saying that it's okay to just not write rad, and you can just say it's pi over 6. We sometimes do that with radians. However, we always write the degree symbol when an angle is measured in degrees. If it's degrees, write the degree symbol. If it's radians, you could write just the number, or you could write the number and rad, or you could write the number and the word radians. Any of those are fine. And by the way, if you have an angle in a problem that you're working on and it says something like theta equals 60, look to see, is there a degree symbol next to it or not? Because if there's no degree symbol, then it's kind of implied that the angle is being measured in radians. By the way, 60 radians would be really weird. 60 radians would be unusual because 60 is actually more common of a measure for degrees. Maybe that wasn't the best example. Something like pi over 2, pi over 3, those are sort of common angles that would show up in radians. I've got a little more terminology to tell you. This is the beginning of a new chapter, so we're kind of establishing notation, terminology, definitions. We say an angle is in standard position if its vertex is at the origin 0, 0, and its initial side is on the positive x-axis. So I'm going to draw a picture here of the x-axis, the y-axis. Here's the origin, 0, 0. And I'm going to draw an angle. Now, an angle needs an initial ray. And we're saying that that needs to be on the positive x-axis, right? And it needs some other ray, which might be called R2. And we think of this rotation like this. And we would say that this angle, that's a little arrow that I drew, a little curved arrow. We would say that this angle is in standard position. What do you notice that's new about this angle that I just drew? This is the first time I've drawn an angle without the unit circle, I think. Well, I guess we had one earlier. All right, technically we had one earlier. That was an angle without the unit circle. But now I'm drawing the x-axis, the y-axis. You might have expected a unit circle to show up, but we can just think of radians as radians and degrees. We could think of angles as existing in the xy plane with their origin at the origin. And we don't necessarily need a circle to talk about angles. But we will talk about circles some more. I have a few more pieces of terminology to tell you, or just little notes and things. So first of all, an angle can be greater than 360 degrees. We said 360 degrees would be if you went all the way around once, one full revolution, and wound it back where you started. And that's kind of like when you go t equals 2 pi. But we know from our discussion in the previous chapter that sometimes you'd have a t value that was larger than 2 pi. You could kind of go around once and then go around twice or whatever. And we're saying the same thing is also true for angles, whether they're measured in degrees or radians. By the way, I want to tell you something. Our discussion of angles in this class might be a little bit different from the way you discuss angles in a geometry class. Okay, and it actually turns out that definitions might be slightly different. I've seen some geometry classes that say, you know, in geometry, they might say that an angle can't be negative, or they might say that an angle can't be greater than 360 or whatever. We're looking at this now from a pre-calculus perspective, and we are going to allow angles to possibly be bigger than 360 degrees. Another little piece of terminology: two angles in standard position are coterminal if their sides coincide. So I'll show you an example of coterminal angles. Well, I want to draw them in standard positions, so we'll have the x-axis, y-axis, and we will make sure that the angle is formed with the origin, 0, 0. So how about this angle right here, which I'm going to say I tried to draw this to look a little bit bigger than 45 degrees. Let's say this is 50 degrees. One angle that this is coterminal with would be if I went around and around I'm going to zoom in on this. See what I did there? I did a rotation. I curved around a full rotation, a full 360 degrees. And then after the full 360 degrees, I went another 50 degrees for a grand total of 410 degrees. So we would say that an angle of 50 degrees and an angle of 410 degrees are coterminal. I'll say theta 1 equals 50 degrees and theta 2 equals 410 degrees are coterminal. Even though theta 1 does not equal theta 2. Do you see the difference between being coterminal and being equal? Because the number 50 and the number 410 are not equal to each other. So be careful about that. Don't say that these angles are equal. They're not. But you can say that they are coterminal. That's why we have a different word for it. It seems like they are equivalent in a certain sense. They're equivalent because the terminal ray is pointed in the same direction. So we call it coterminal. Now, I said we were still going to talk about circles a little bit. We're not completely done with our discussion of circles. I want to talk more about how angles and circles are related. How about this? We've seen how circles can kind of tell us things about angles. Maybe we could see how angles could tell us some things about circles. So what I'm going to do is let theta equal an angle measured in radians. For the purposes of this discussion, we're specifying that it's measured in radians. Let r equal the radius of a circle. And we're going to draw a picture of this too. So if it's not clear what S is, it'll be clear in a moment when I draw it. S is going to be the length of the arc formed by the angle theta. So I'm about to draw a picture of this scenario. And one thing that is worth pointing out is that I'm saying r is the radius of a circle. I feel like in this class we've been talking about the unit circle for so long, and the unit circle always has a radius of 1, that we start to forget that, other circles exist. Yes, we could have a circle with a larger or smaller radius. So let's say this is a circle with radius r. And, it could be 1, or it could be 2, or it could be 1/2, whatever. We're just calling it r. And we have an angle measured in radians. Let's draw this angle in standard position just to make it simple. So how about this angle? I'm going to label it here. I'm going to put the little angle symbol, and I'm going to write theta. So what is this thing S that I'm talking about? The length of the arc formed by the angle? The arc is going to be this length here. It's a curved length, and we're going to say this length is S. All right. Now, how are these three quantities related to each other? They're three different numbers, and we have a simple formula. We have a simple formula for how they are related. It turns out that theta is equal to S over R. Simple formula. Now, I want to warn you, this formula only works if theta is measured in radians. So I specified that theta is measured in radians. It does turn out that that's important. Otherwise, the formula doesn't work. But if you had an angle that was measured in degrees, you could always convert it to radians and then use this formula. So in that sense, the formula would still work as long as you convert it first. Another formula I'll tell you is that you could take this and rearrange it in a couple of different ways. And one way that's convenient is multiply both sides by r to get this. These are both equivalent to each other, right? Just rearranged. By the way, in the first formula that I wrote, where theta is S over R, we don't really have to worry about dividing by 0 because a radius of a circle can never be 0. So we're okay to divide by that. Underneath, a little piece of terminology, we say the angle theta is subtended by an arc of length S. So if you see that word subtended, that's what we mean. We just mean that the angle theta corresponds to an arc of length S. I'll show you a problem that uses these formulas. So we're going to do some problems for the rest of this section. We've got everything we need to answer some different types of problems. Let's start out with... Oh, actually, you know what? We might need one more thing before we do some certain types of problems. But let's do a problem based on this. So I'm going to say, find the length of an arc of a circle with radius 9 feet that subtends a central angle of 45 degrees. Why don't you try this one? How about you pause the video, give this a try. All right, so first thing that I was hoping that you would notice is that this problem, it gives you an angle that's in degrees, and we just said a few minutes ago that that formula above, it only works if you're in radians. So we want to take the 45 and convert it into radians first. So 45 degrees times pi over 180 is pi over 4 radians. And now we can use the formula. So use theta equals pi over 4, and we'll be in good shape. So the formula that I want to use, we're trying to find the length of the arc. So we're trying to find s, and the formula is s equals r theta. It's just going to be 9 times pi over 4. Well, what can we call this? I guess we could just say 9 pi over 4, and we'll say feet, because this was measured in feet in the original problem. So what kind of circle could you think of that's 9 feet? It's kind of like a, I don't know, small swimming pool or something. It's a pretty big circle. If you drew a picture of this, you might have a 9 here and a 45-degree angle. 45. Oh, I'm drawing this really small. Let's zoom in on it. All right, so you've got a radius of 9 and a 45. And the question was asking for s. The question was asking, what is the length of this arc? So what did we find? 9 pi over 4. I'm going to tell you with a calculator, I found that this is approximately 7.1 feet. Now, I like the answer the way we put a box around it, because that's the exact answer. It's exactly 9 pi over 4 feet. The reason I checked it with a calculator here is I found that it's 7.1 because I was able to look at this picture and ask myself, does 7.1 kind of make sense? And yes, I think it does. I think if the radius is 9, then I was expecting that this arc would have a length that's a little bit less than 9. So everything seems to check out. We answered the problem. I just wanted to see if you would notice that you needed to convert to radians first, and then you're basically just multiplying it by 9. All right, now there is another type of problem that I need to tell you a couple of preliminary things before we can do problems. So, question, we'll just make question. There's only one question, really. And that is, what is the area of this region? And as an example, I'm going to use the same kind of region that we just drew, but I'm going to draw a bigger picture of it because it was so small in that problem. And you know what else? I think that for the sake of this, I will leave off the feet. I'll label this 45 degrees. And I'll round off s to just 7.1. It's actually 7.1 with some other digits, but I'll just round it off to 7.1. And I'm talking about the area of this kind of region that we cut out from the circle. Do you think we could find that area? One thing that I want to warn you about is that this is not a triangle. Okay, I've seen some students try to use like formulas for triangles. This is curved. This is curved here, right? So it's not a triangle. It's like a pizza slice, right? With a curved border. So, well, one thing I'll say is that we know the area of the entire circle. What's the area of the entire circle? That's pi times the radius squared. That's the formula for the area of a circle with radius r. Well, we have theta, which is 45 degrees, which is pi over 4 radians. It's okay to put an equal sign between them. They're just two different units of measurement. Theta is 45 degrees, which equals pi over 4 radians. And I know that it would take 2 pi radians to go all the way around the unit circle. What portion of that have we gone? We went to here, and we stopped. I'm going to say that this is 1/8 of the circle. Can you see that in the picture, that the highlighted region is 1/8 of the entire circle? I guess mathematically you could say it's because pi over 4 over 2 pi simplifies to 1/8. Or because 45 degrees out of 360 degrees simplifies to 1/8. Either way, you could figure out that this region is 1/8 of the entire circle. So if we know how to find the area of the entire circle, we would just find the entire area and then multiply it by 1/8. So the area of the region is, let's be more general here. This thing that I did here, I put theta over 2 pi. So the area of the region is going to be theta over 2 pi times pi r squared. Right? That's going to be me doing basically 1/8 of the area of the circle. We take this and simplify it, and we get a formula for the area of this type of shape. And it's going to be, well, there's a 2 on the bottom, but the pi and the pi cancel out, right? So we could write this as 1/2 r squared theta. And that's how we usually write it. So this is another formula that can help us with certain types of problems. We call this region a sector of the circle. Okay, so it's a portion of the circle cut out by a certain angle, subtended by a certain arc, and the circle has a certain radius. To find the area of the sector, you need to know the radius, and you need to know the angle. And I'm going to say, again, theta must be in radians to use this formula. Because otherwise, you'd be multiplying by something like 45 degrees. If you multiply it by 45, your answer is going to become enormous. We want to be multiplying by something like pi over 4, and we get the appropriate answer. Here, I'll show you a problem. This was basically, the question was, could we figure out a formula that answers this question? And we figured out a formula, so now let's do a specific problem. I'll do this one for us, and then I'll have something else for you after this. So let's find the area of a sector with central angle (210 degrees) if the radius of the circle is 3 meters. I'll do this for us. Just give you a chance to see that if you're writing it down. So we could draw a picture of this if we want to, but we don't even really need the picture. We're going to wind up using this formula. Does the picture really matter? I don't know. First things first, I'm going to convert this angle into radians. 210 times pi over 180. Because I know that the formula that I want to use needs radians. What's 210 divided by 180? Well, cancel the zeros, and it's 21 over 18. 21 over 18, they're both divisible by 3. you should be able to simplify this to 7 pi over 6. Now that's 7 pi over 6 radians, but this time I'm not writing rad. I'm just leaving it because we said that with radians, it's okay to do that. All right. Now I'm going to use that formula that we had above. A equals 1/2 r squared theta. And in this case, it's 1/2 times 3 squared times 7 pi over 6. And then we just simplify this and see whatever we get. 3 squared is 9. Let's combine it with the 1/2 and make it 9 halves. And then we have 9 halves times 7 pi over 6. Now, there should be a certain unit of measurement, right? But I'm okay with just leaving the units of measurement off, and we'll just make sure that the final answer has the unit of measurement. This is going to be an area. This was in meters. So I think our final answer is going to be in square meters. What do we do to simplify this? There's a 9, there's a 6. Maybe we can like simplify that a little bit. 9 and 6 are both divisible by 3. The 6 would become a 2. The 9 would become a 3. 3 times 7 is 21. 2 times 2 is 4. So 21 pi over 4 meters squared. And that's the answer. So that's the type of problem that this formula might get used for. So in this section so far, you've seen 2 formulas that I think you need to memorize. There's the one for, theta equals S over R. And that's just for basically an angle, a radius, and then the length of the arc. And that one has nothing to do with area. That's just about lengths. But if a problem is asking you about area, then it's probably asking you for this formula. Or I guess you could see a problem that asks you both, like gives you some circle and maybe asks you to find the area and also might ask you to find S. All right, I'm going to give you a problem to try. You know how I said that a sector of a circle is kind of like a slice of pizza? It's not a triangle because it has a curved edge. So this problem is going to say an apple pie is cut into 12 equal slices. If each slice has area 3 pi inches squared, what is the radius of the pie? And before you try this, I'm just going to say, because in math we like to be very clear about things, assume the pie is a circle. All right, so go ahead and give this a try and pause the video and see what you can come up with. Okay, so I decided to draw a picture for this one. I just drew a circle, and then I tried to cut it into 12 equal slices. So how do we do that? Maybe we cut it like this. We've cut it into 4 pieces, and then each of those 4 pieces needs to be cut into thirds. So maybe do something like this. It's okay if it doesn't look exact. All right, 12 equal slices. Now the area of the entire pie is pi r squared, okay? This problem is asking us what is the radius of the pie. And That's what we need to find. Now, I know that each slice has an area of 3 pi, so maybe you could think of it as like, you know, this one has an area of 3 pi, this one has an area of 3 pi, and so on. I'll say dot, dot, dot. Each slice has an area of 3 pi, and there's 12 of them. There's 12 of them, so the entire area of the pie is 12 times 3 pi. See what I did there? Slice, area of one slice times how many slices there are. Total area of this circle is this. So 12 times 3 is 36. So this is 36 pi equals pi r squared. Oh, we have pi on both sides. Let's cancel it out. Pi and pi cancel out. So 36 equals r squared. We're trying to solve for r, and I get r equals 6. And then I take a quick look at the problem to figure out what's the unit of measurement here. The lengths were measured in inches, so this is going to be 6 inches. That's the answer. You could check your answer. Let's do that. Let's check our answer. Let's check with this formula. So does the area of one slice, does this work to get us the area of one slice? So 1/2, we're saying that the radius is 6, and what would theta be here? We answered the problem, by the way. I'm just thinking about how I would check this. What do you think theta would need to be? Well, if we're going to get 12 equal slices, we could do this angle, do it again, do it again. It looks like there's 6 of them by the time you get over here. You can use what you know from previous lessons from the unit circle. Even though this is not a unit circle, it's still a circle. And I think that the angle that we're talking about is pi over 6. This angle is pi over 6. It takes 6 of them to get halfway around. And we know that going halfway around is pi, and going all the way around is 2 pi. So yeah, that looks good. This says 1/2 of 36 times pi over 6. 36 over 6 is 6, so let's start simplifying. 1/2 times 6 times pi. I get 3 pi. What was I checking? I was checking to see if I would get this, and I did. I did. Everything checks out. So if the radius is 6 inches, then we do get the correct area of a slice. This was optional, checking our answer. But, it's one of the nice things about math classes is that if you have time, sometimes you can check your answer. Okay, I'm going to give you one more problem. I'm going to give you a tougher problem to think about. So I think I'll move this off of the screen. So, pause it if you need to copy anything, because I think we need a fresh sheet of paper for this next problem. There's going to be a big picture. All right. Something for you to try. Let's see. Should I explain the problem in words first, or should I draw the picture first? I'll draw a picture, and then there's going to be some sentences to the side of it. So we're going to have 2 circles. Okay, good enough. There's an origin. Going to say that this angle is 45 degrees. This is all given to you. There's going to be a question here. So wait till everything is written. I'm labeling this 4. I'm labeling this X. All right, the length of the inner arc is 4. Find the length of the outer arc, labeled X, if the outer circle's radius is 2 greater than the inner circle's radius. And I'm gonna tell you, this is a harder problem, but we've covered everything you need to know to answer this. So I'd like you to pause the video and give this a try. All right, so we know that what we're looking for is a number. X is a number. Oh, and this said that the length of the inner arc is 4. It didn't really say, some length of, some unit of measurement. It didn't say 4 inches or 4 meters or anything like that. It's just 4 units. So I'm expecting X to be some number. From the picture, I would guess that X is going to be larger than 4. But how much larger than 4 is it? Is it just 4 plus 2? Well, probably not. Probably not that simple. Here's what I'm going to do. Both arcs that we're talking about, there's 2 arc lengths. There's the 4 and there's the X. What do they share in common? They share in common the angle. So the angle is pi over 4. I've already converted this to radians. 45 degrees converted to radians. And, you wind up getting used to some of the common angles that we deal with, like 45 degrees. It's pi over 4, and you wind up just doing those conversions very quickly. Let's say something about the inner arc, because I think from the inner arc, we know the 45, we know the 4. Do we know the radius of the inner circle? Let's start writing some stuff. Inner arc. The inner arc should follow the formula theta equals s over r. So maybe we can figure out the radius of the inner arc. And then the radius of the outer arc is going to be 2 more than whatever this is. I'm going to take this and use a rearranged form of it. We could rewrite this as s equals r over theta. Does that help us? I mean, I'd like to find, I know theta, I know s. I would like to find r. So maybe I'll rearrange this yet again to get r by itself. R is equal to s over theta. I like that. Let's use that version. R equals s over theta means the radius is 4 over pi over 4. That's the radius of the inner circle. Can we simplify that? 4 over pi over 4? Yeah, instead of dividing by a fraction, we could multiply by its reciprocal. That's how I like to deal with a fraction inside a fraction. So this is going to be 16 over pi. And I don't need to write inches or feet or anything like that because it's just, that was 4 units. So this is 16 over pi units. Now, that's not what we were looking for, right? But I found a piece of information that wasn't given in the original problem, and maybe it's going to be useful. Now we know everything about the inner arc and the inner circle. The inner circle's radius is this. So the outer circle's radius is this plus 2. Let's talk about the outer arc. Let's write everything we know about the outer arc. We know that the angle is pi over 4. We know that the radius is 16 over pi plus 2. And S is what we're looking for. It's labeled X, right? That's what we want to find. So X, which in terms of the formula is S, is equal to R times theta, right? This is the little formula that we know. But now I'm talking about the radius of the outer circle. So the radius of the outer circle is this thing. So it's going to be 16 over pi plus 2, that's my radius, times pi over 4. We're almost there. We basically have found X, and all that's left is to try to simplify this answer. I think we should distribute across the parentheses. So 16 times this, 2 times this, right? Let's do that. So 16 over pi times pi over 4 plus 2 times pi over 4. How does that simplify? Pi over pi cancels out. Pi over pi. All right, 16 over 4 is 4 plus 2 over 4. Don't leave your answer as 2 over 4 pi. I don't want to see an answer that has 2 over 4 in it. You should know that 2 over 4 is 1 over 2. So this is pi over 2. And that's the answer. 4 plus pi over 2. Pretty cool. This was a kind of an interesting problem. This is, I'll tell you, kind of a unique problem. I don't know if you'll see one exactly like this, but the tools that we've established in this section allow us to solve a variety of unique problems, you know, this being one of them. It turned out that this used the formula for the arc subtended by an angle. It used it twice, once for the inner arc and once for the outer arc. And I think that what really helped was finding the radius of the inner circle so that we could just add 2 to it. So, cool problem. I like it. Answer that we got is 4 plus a little bit more. And looking back at the picture, I told you that I thought the answer was going to be a little bit bigger than 4. Because, you know, how could it not be? This is 4. This looks bigger in the picture, so it's going to be bigger than 4. 4 plus pi over 2. Cool. All right, so that was our section on angle measure. So remember, we are actually still talking about trigonometry. I think when people hear trig, they think of a lot of different things. Some people hear the word trig and they immediately think of sine, cosine, tangent, and the others, cosecant, secant, cotangent. To some people, that's what trig is. But really, that's one facet of trigonometry. But trigonometry is about circles, it's about angles, it's about triangles, it's about sine, cosine, and tangent. We just talked about angles, and in the next video lesson, we will talk about triangles. And we're going to talk about triangles for a couple of lessons. So just to give you a heads up of what's coming soon, The next video lesson will be about right triangles, just right triangles. And then the one after that will be about probably about more general triangles that are not necessarily right triangles. Okay, and we'll see sine and cosine and tangent and the others. They'll show up again. Okay, so that's it for today. Thanks for watching, and I will see you next time. Take care.